Hello everyone, welcome to Dr. Ravi's Academy. In today's lecture, you will be understanding how to determine the deflections of a simply supported beam by Macaulay's method. And in this particular method, we will be using a generalized bending moment equation. So for that purpose, what you have to do is you have to find out support reactions RA and RB for the given beam. Let us look at that. It is subjected to 2-point loads and you have to use equations of equilibrium. I am using it is sigma ma is equals to 0. Moment sum about left hand support. I am treating anti-clockwise moments are positive. So with this notation, your 120 kilonewtons and 80 kilonewtons both are contributing clockwise turning effect. That becomes negative. So 120 into moment arm is 3 meters. Again 80, the moment arm is 3 plus 6.5, that is 9.5 meters. And these two are contributing clockwise turning effect. And your support reaction RB is contributing anti-clockwise, which is positive, and the moment arm is 14 meters is equals to 0. So this is your equation of equilibrium. With this, let us find out RB. So you are going to get RB value as 80 kilonewtons. So this is first step, and substitute second equation of equilibrium, that is sigma Fy is equal to 0. In this, your Ra plus Rb is equals to 120 plus 80, and from this you can calculate Ra as 80 kilonewtons. So you got both the support reactions. Ra is 80 kilonewtons and Rb you got it as this is 80 kilonewtons and the left one is 120 kilonewtons. Right? Now you have to select a generalized bending equation, and in which all the loads you are going to consider. I am writing this, selecting a section, I am calling it as Mn at a distance x from the left support. I have taken this particular section just before the right support, and let us write down mx equation with standard notation. As you know that mx is equals to, as you know very well that the smile effect bending moment is positive. With this notation, let us write the bending equation. Your Ra 120 kilonewtons contributes smile effect, so it is 120 into x, which is positive, and 120 kilonewtons, that is contributing anti-clockwise turning effect. So it is a sad effect of it. It is minus 120 into the moment arm is x minus 3, and lastly your 80 also contributes a sad effect, and it is minus 80 into x minus 3 plus 6.5. So this is the moment arm. So you are deducting 9.5 from this, and this is what is your generalized equation for the bending moment. And you will be using Newton's formula for the curvature, and that equation is EI times it is d square y by dx square is equals to minus mx. So this equation you are using, and for Macaulay's method, let us substitute mx equation, mx value into that. You have EI times it is d square y by dx square is equals to minus mx, multiply with minus, you have minus 120x, your minus becomes plus, that is 120 x minus 3, and this also becomes plus x minus 9.5. So this is your equation, and integrating you are going to get slope equation, and further integrating you are going to get deflection equation. So this equation is EI, this becomes dy by dx, nothing but slope, is equals to, remember that in Macaulay's method you will be writing the constant of integration in the beginning. C1 is the constant of integration, and here 120 integral of x is x square by 2 plus 120 x minus 3, integral of this is x minus 3 square by 2 plus 80 x minus 9.5 square by 2. So further you can simplify, it is a C1 minus 60, it is x square plus 60 x minus 3 square plus 40 x minus 9.5 square. This is your slope equation. And further integrating, let us integrate further. You have, it is EI into Y deflection. The deflection is a second constant of integration. I am writing it as C2 plus C1. Integral of C1 is C1x minus, it is 60 into x cube by 3 plus 60 x minus 3 cube by 3 plus 40 x minus 9.5 cube by 3. So this is the equation for the deflection. So you write down the simplified equation. You have C2 plus C1x minus 20 x cube plus 20 x minus 3 cube plus 40 by 3 x minus 9.5 cube. This is your deflection equation. In this you have to find out the constant of integration C1 and C2. If you substitute the conditions, boundary conditions, deflection at the beginning at A and B both are 0. That means your x value is 0, y is also 0, deflection is 0, and at x is equals to L, your deflection is 0. So these two are the boundary conditions for the deflections. Using that you can find out, if you substitute x is equal to 0, y equal to 0, automatically your C2 will be 0. C2 is 0, and substituting x is equals to L, that is 14 meters, you are going to get C2 value, and in this equation you have to use EI equation. Here Young's modulus is given 210 kilonewton per mm square, and the moment of inertia is given 16 into 10 to the power 8 mm to the power 4. So you can calculate EI value, that is it is 3,36,000 kilonewton meter square. So this value, if you substitute into this and substitute at x is equals to the value 14 meters, you are going to get a C2 value as 1932. So C2 value is 1932, and now after knowing this C1 and C2 value, C2 is 0. This is C1, C2 is 0. By substituting x is equal to 0, you got C2 0, C1 value is this, right? And he is asking deflection under the point load 120 kilonewtons at C and under the 80 kilonewtons at point D. So at x is equals to 3 meters, your YC value deflection under that you are going to get in this equation 15.6 mm. And similarly at x is equals to, he is asking under the second point load 3 plus 6.5, 9.5. So if you substitute 9.5 mm, it is meters, you are going to get the YC is 19.9 mm. So these two are the answers of your problem. I hope you have understood this particular Macaulay method. Let us apply for any problem this particular method. You are going to get the solution for it. Thank you.